Hi everyone. My name is Mounika. I'm an assistant professor in AML department of Tigala Krishna Reddy Engineering College. Now I'm going to explain you about the node reduction algorithm in software testing process management. So what is a node reduction and why we are doing the node reduction means from the starting from the entry to exit only the single path expression should be there. No any other multi-purpose and multi-node should not be there in the link. So for that purpose, we need to reduce the nodes. So we need to eliminate the nodes. One by one, we need to eliminate the nodes. So how we eliminate the nodes, we need to see now. And let me share the copy. Let me share the copy. I think it is visible. See, first is a path products here. We are seeing the path product. What is the meaning of the path product? A path product is a combination of several path segments. That means it is a combination of different segments. Likewise, here we are seeing, see, 1, 2, 3, 4, 5. These are the path segments. So these path segments are the combination. So the definition is it is a combination of all the path segments. So here each segment of is given a name. What here we have given the name as 1, 2, 3, 4, 5. These are the path segments. So see here the path is expressed as the concatenation of all the path segments of the path. Concatenation means what? Concatenation is nothing but combining. Is a combining of all the path segments. The product obtained for the path after concatenation is known as a path product. Whenever we combine all the path segments, then we will be then the product which we obtain is known as a path product. So see the example here. See the example here. The nodes are 1, 2, 3, 4, 5 up to 5. So totally 5 nodes are there. So see in the from the above figure there are 4 path segments. What are there? A, B, C, D are the path segments. The path from the node 1 to 5 can be expressed as a concatenation of A, B, C, D. That is A, B, C, D. That means we have to do the product. We have to do the multiplication of all the path segments whichever we are seeing in the whichever we are seeing in the segments. So now next, for example, see the other one. If A and B are the path segments, then A is equals to ABC and B is equals to B is equals to DEF, B is equals to DEF, then the path product would be the combination of A and B. That means we have to do the multiplication of both A and B segments. So here A is ABC and B is DEF. See. So next, what is the concatenation? We need to multiply these both A and B. So the path product, what we obtain here is A, B, C, D, E, F. Okay. Next one, how we represent the next thing? If A and B are the set of paths represented as, if suppose they have given A is equals to AB plus CDE, AB plus CDE, then B is equals to PQR plus ST. So next, what is the combination of these both path segments? That means we need to product this A and B. So first we need to write A1, the A belongs to data and the B belongs to data. The both the data should be again concatenated. That means it should be uh, multiplied. So what we obtain here, ABPQR plus CDEPQR and ABST and CDES. Just we are doing the multiplication. That's it. Just we are multiplying. Next, what are the properties here? The path product is a not commutative. That means it is not commutative. That means AB is equals to BA is not equal to BA. That means AB is not equal to BA. That is implies if A and B are two paths, then AB is not equals to B. Next, path product is associative. He is saying associative. That means it obeys the associative law. If A, comma B, comma C are three paths, then A into BC is equals to AB into C. That is equals to ABC. That means however we take A into B and C or A of BC, whatever, however we take, it will get the same thing. Next, what is the meaning of a path expression? The path expression which represents the set of all possible paths between an entry and exit nodes is known as a path expression. That means all the set of the possible paths. That means how many paths we are getting from entry to exit. For suppose imagine that five paths are there. So this combination of all these comes under this path expression. So consider this example here. The path expression consists of a path names and the plus means or symbol. I mean he is saying he is to addition. Example C here. From first node to fifth node. How many links are there? From 1 to 2, A is there, 2 to 3, B is there, and a self loop C is there, and 3 to 4, D, and self loop of 4 is E, and from 4 to 5, F. So if we consider the node 1 as entry node and the node 5 as exit node, the number of paths available between 1 and 5 are, see the combination here. A, B, C, D, E, F. Next A, B, C, C. Why C, C means self loop is there again. A, B, C, C, D, E, F. Next combination is A, B, C, C, D, E, E. Why again D, E? Here self loop is E again. So up to so on we can take up to how many possible paths are there, that many we can take. Next, their path expression would be AB. That means how many paths we are taking here from entry to exit, how many path segments are calculated. Those are we have to do the product of all the path segments here. So that's why we are doing here addition A B C D E F plus A B C C D E F plus A B C C D E F. So next, if any of the link is repeated, it can be represented in terms of power. That means if the link is repeated again and again, so that can be represented in power in terms of power. If the power is 0, then there is no link. That means A power 1 will be obviously 0. A power 2 is double A. A power 3 is triple A. Up to so on A power n, he is saying A up to n times. Applying this, the both path expressions can be expressed as ABCDEF plus ABC square DEF plus ABC square DE square F plus up to so on ABC power n DE power n F. Possible paths will be there. Next, what is the meaning of path sum? What is the meaning of path sum here? The parallel path segment in the path indicates that the flow can occur in any one of those parallel paths if it is represented by over or sum. In other words, the path sum is the path between parallel links between the two nodes. See the example here. From first node to second node, only a link is there. That is direct link. And from 2 to 3, from 2 to 3, how many links are there? 1, 2, 3, 4, 5. So these 5 links are in parallel way. So this comes under the parallel link. So we need to add the parallel. Whenever we see that several parallel links are there, then we need to do addition. First of all, we need to do addition. Next, from third node to fourth node, G link is going. Next, if the path between the nodes 2 and 3 are considered, there are 5 parallel links. How many? C, D, E, F, like this. Total 5 are there. He's saying what we have seen earlier. He's saying that again. The path between those two nodes would be represented as addition. That means A plus, B plus C plus D plus E plus F. The entire path would be represented as A of B plus C plus D plus E plus F into G. That means why we are taking product here? It is in the form of a series. First of all, we need to do sum between this two second and third node. Next, after getting some expression, we need to multiply it with the other segments which are in parallel with that. So here the combination A into B plus C plus D E plus F into G. We have to do multiplication for all the things. That's the product we have obtained here. ABG plus CACG plus ADG plus AEG plus AFG. Next, what are the properties here? The path sum is with commutative. It is a commutative, whereas here it is not commutative. Here it is a commutative. Okay. Next, it is a associative also. That means the combination of A plus B plus C is equals to A plus B plus C and A plus B plus C. All the things will become the same. Next, what is the meaning of the loop here? It is said to be loop when the same link is repeated infinite number of times. When the loop is repeated infinite number of times, that is known as a loop. Or it can be considered as infinite number of parallel path also. A loop can be result in never ending termination of the path. If the loop and link can occur 0, 1, 2, 3 up to infinity times, the occurrence of the occurrence can be represented as a power 0, a power 1, a power 2 up to so on a power n. Okay. In general, it is represented as a power star also. That means here star indicates that an element occurring 0 or more times. For example, see the example here. Here from first node to second node, A path segment is going in a straight away in a serial manner. Next, 2 to 3, B node. Next, at third, we are having the self node, that is C, and next third node to fourth node, D is going. Again from fourth to fifth, E is going, and again from fifth node to fourth node, again the F link is coming. See here. So this type of the situation is known as a loop on path expression. So this can be solved by using first we need to multiply E into F, then we need to do whole star. So how many times it will be repeated? That many times we have to place the number in the place of star. Next, fifth node to sixth node, G is going. For example, there are two types of loops. There are self loop and loop on path expression. As we discussed here, two types of loops are there. This is a self loop, this is loop on path expression. Self loop means in this figure, the self loop is the node 3 as we seen here. Self loop is a node 3. The processing of the loop which retains the same state is known as a self loop. That means it is started from the node itself, it is ending at that node itself. The loop on only one node and itself is known as a self loop. It can be represented as C star. The loop on this path expression is the repetition of the same path occurs again and again, then it is known as the loop on path expression. Here from fourth node to fifth node, E went again from the fifth node to fourth node, again F is coming. So that's why it is known as a loop on path expression. For this example, node 4 and 5 in the figure 5.4 can be considered as a loop on path expression. Next, it can be represented as I said before, E into F power star. If the loop value cannot be 0, then it has the minimum of one repetition, then it denoted as a power star. A into a power star is equals to a power star into a is equals to a plus. A plus denotes the occurrence of the elements one or more times. Okay. Next, so depending on these all rules, that means how this path product is done, how the path expression is done, how path sum is taken, how loops are there. So these all the things we have to remember and we have to keep in mind. And next we need to reduce the node reduction. So we need to reduce the node reduction by using these all rules. That means the series rule, the parallel rule, and the loop on path expression. Next, we'll go for the example now. See, the node reduction procedure is a method to find out the relationship between the starting and the ending node in terms of algebraic expressions. That means we need to find out the relation from the entry to exit. We need to find out a single relation between the entry and exit. So we need to solve the expression to reduce it to the a single expression. That means only one entry and one exit should be there. No multiple entries and no multiple nodes should be there. It is done by removing the node by node. If it is in such cases, we have to remove node. What is the goal of this node reduction procedure? The main goal of the node reduction process is to reduce or remove all the intermediate nodes between the entry and exit nodes and find the algebraic notation which is helpful in process of debugging. So what is saying here? Mainly here we need to reduce the node. That means we need to delete the nodes where are the intermediate nodes. Intermediate nodes means from the entry to exit, whatever and how many are there, that many we have to reduce them. So for that we need to have one procedure. What is that procedure? See, to reduce the nodes, the sequence of the steps that we need to take place are the following. See, the step one, all the series links in the path can be multiplied or concatenated in the path expression. First, we need to solve the serial links. Next, step two, all the parallel links in the path can be added with the path expression. As earlier in the example we have said, the parallel links are there, we need to do the addition. Next, in step 3, all the self loops in the path can be eliminated by replacing them with the expression like a power star. So like a self loops, like a loop on path expression, we need to solve as a as taking that into consideration. As a, if it is self loop, we have to take the self loop segment whole star. If it is a loop on path expression, we have to do multiply of that path segments and to keep the whole star. And step 4, in the remaining nodes, in the remaining nodes, choose any one of the node which is not entry and not exit, that should be removed. The path expression of the inlinks and outlinks of the chosen node should be multiplied and direct link must be placed with the product of the path expression. So what is saying, first we need to remove the node which is not having the entry and exit nodes. So which one we have to take? With the last one which we are going to eliminate, that should be in a blurred one, and that should be eliminated by taking the necessary rules like serial expression or parallel expression or any other we have discussed earlier. Next, step 5. The removal of the node in step 4 may lead to some other serial link or the parallel link and the loops. Remove the serial links by concatenating them. So what is the meaning of concatenation here? We need to combine the serial links. Wherever the serial links are there, then we need to concatenate them. Next, step 6. Remove all the parallel loops by adding them as done in step 2. So we need to remove the parallel loops. So compulsory we have to remove the parallel links. Why? Because if we don't remove the links, what happens? Obviously, the link may not get disturbed, and intermediate nodes will be arises in the same manner. So next step 8. Check whether a graph contains a single link between the entry and exit node. We have to check whether the entry node and exit node are having a single link or not. If the single link is not there, so where the link is going to fluctuate, there we have to again we have to do the node reduction procedure. So if exists, stop the process, or else continue the process till all the nodes are removed and only one link is present. Till only one link is present, till that we have to do the whole process again and again and again. The path expression of the final single link would be final path expression. Path expression. Finally, what we get a single link is a final path expression. So see, consider the example here. 1, 3, 4, 5, 6, 2, 7, 8, 9, 10. These are the nodes. These are the nodes we are taking in this example. So see here, the entry node is here. 1, the exit node is 2. Here, we need to eliminate all these intermediate nodes, whichever we are having here. Totally 8 nodes are there. So, one by one, we have to remove the node. First and foremost, we have to remove this 10. See, for the 10th node, the incoming links what are there, outcoming links what are there, we have to check first. Here the incoming is J part segment is there, that is coming from the 5th node, and from the 10th node, the L path is going to 7. So these both are in series manner. So if it is in series manner, what we need to do? We need to concatenate. That means we need to multiply both the path segments. So that's why here we have done J and L. So we have to eliminate this 10, and we have to keep the dotted lines just for the just for to know what is the link here. So here 10th node is removed. Next, from the above figure C, next elimination chance goes to the 9th node. Here for the 9th, incoming are from K, that's it. From the that means here K, M is there, and next from 4th node also other link is coming. Here we need to eliminate it by using the rules as a parallel rule and series rule. Here the 9th node is also eliminated. In the same way, we have to check with the 8th node. Here the 8th node is in the flow graph. Whatever the incomings are there, whatever the outgoings are there, we need to check. Simply we have to see how. Simply we have to see how to see the solve the serial links and how to solve the product link. I mean the parallel links. That's it. So if you know perfect about that parallel link, series link, and the loop and path expression, you can do perfect manner. So this process will be continuous until see after the 8th node is deleted, next 7th node. After the 7th node, next it will be eliminated. Which one is eliminated next? 4th node will be eliminated. Next is 5th node, and next is 3rd node, next 6th. See, up to last, only single link is there. From entry to exit, only single link is there. So this is the final flow graph. This is the final flow graph we are seeing here. This is the final flow graph. So this is the node reduction procedure. Simply what we have to do, we need to know the rules which we are following here. First one is the path product. That means whenever we see the path segment in the series and in the serial manner, we need to concatenate. That means we need to multiply. If the link is in the form of the parallel. We need to do the summation. That means we need to do addition of the path segments where the parallel links are there. Next rule is the loop on path expression and the self loop. Self loop means what the path segments we are accepting as self loop, that power star. And next, loop on path expression is how many path segments are there, that into the path segment multiplication power whole star we have to take. So remembering all these three expressions and these three rules, it will be easy to remove the node reduction. That means we can remove easily. That's all for today. Thank you.